So, hello everybody. Good afternoon. I hope you can hear me correctly. In case you have any issue, please let us know in the chat. And welcome to this second session of our training webinar series that we have dedicated to the topic of powder metallurgy in the green transition. And well, incredibly, on the same date as last year, this is just by chance, but we started on 20 March 2024 with the first session, and now we are again on the 20th of March. Don't expect that to be the rule. We have three speakers today, again with three different topics as like last year. One is dedicated to sustainability of additive manufacturing. The second lecture is on recycling of hard metals. And the third one is dedicated to soft magnetic composites. And they're all topics that are very well related to the green transition that Europe is trying to have in the next decades, and that should lead us to a cleaner Europe, better and more sustainable production, and finally even better products. I will take the first 20 minutes of this session to explain you something about EPMA, and especially for the non-members, and the activity that we run every year. I will not go in much detail. I would like not to spend too much on this, and leave more time for the lectures. And yeah, I think we should start really, so that we can then come to the technical part as soon as possible. So let me move back to my corner here and start sharing my slides. And again, if you have any issue, please let us know through the chat. The chat should be used also as much as possible to communicate with us about the possible questions to our speakers and lecturers. So when we will have the Q&A, I will switch to a situation where anyone in the audience can switch on the microphone and camera and come to the stage. But if I don't know that you are doing that, maybe it's better if you just type something in the general chat. What else? Yes, and then you have to prepare for the test at the end. So please keep in mind that you will have to answer some questions, not terribly difficult probably, but you better take notes during the lectures. And I hope you enjoy this session. So let's start with my presentation then on the topic of EPMA. And first of all, who we are the Association for Powder Metallurgy in Europe. And this is since 1989, so we already celebrated our 35th year last year, and we're going towards our 40th in a few years. We have the mission of representing the PM community and fostering its development. So whenever it's needed in Europe or internationally, we represent the PM community and want to promote and develop powder metallurgy in Europe, and not only, if possible. It's a win-win situation normally. Developing the future of our community. And we try to do it as much as possible being steered by the members. So we have an assembly of members, we have a council, which is composed of important companies in the sector in Europe, and a board, a president. They are all members and not coming from the staff of EPMA. So the membership is actually covering the whole supply chain for powder metallurgy. That means starting from the powders and going down all the way to the production of parts with those powders, and also we have some end users there. Clearly, to do this, our members need the support of specific equipment. So also these, some of you come from this sector, are included in our membership, equipment manufacturers. And last but not least, because it represents almost 1/4 of our membership, it is the R&D sector in Europe that is, I would say, quite well linked to the production companies, and there is a good synergy between the two. So the membership is actually composed, as you see here, by activity. More or less 1/3 of the companies are producing parts. It's those that you see here in this area, 1/3. Then there is, as I said before, 1/4 dedicated to research, and this includes also individual members. Clearly, universities normally are much bigger entities and don't join all the associations for the work of their professors and researchers, and then we allow individual members to come from that area. Then we have raw materials producers, and this is also an area. Raw materials, normally we here intend powders or other supplies for the production, but of course we could extend this to the ores and the materials that are used by the powder producers to produce their powders. And then you can see also consultants and users and other categories. In terms of geography, on the right, you see that Germany has the lion part of our membership, and then we have many other countries in Europe with about 10%. And we also have some members overseas, and some of you actually come from outside of Europe here. They have different rights. For instance, they cannot vote in the assembly, but we accept members from outside of the European continent. We do a lot in terms of events. Here are the events that we have organized for 2025 in terms of seminars and training. And the first one is the one that you see. That's the one where we are right now. Then we have a couple of seminars, one dedicated to, this year dedicated to application sectors. So there is an aerospace seminar in May and the medical seminar in October. And you've probably seen the advertisement when we were waiting for the session to start. So please consider joining these two events. And then we have another important event, which is linked to training, which is our powder metallurgy summer school. It's almost a full week dedicated to training on powder metallurgy, all topics of powder metallurgy. And it will happen this year in Lund in Sweden in June. But of course, the most important event that we organize every year is the Congress. The yearly Congress goes under the name of the label of European. So European 2025 will be in Glasgow in September, mid-September, a little bit earlier than normal. We normally have the Congress in October, but this year is in September. And yeah, it will cover the whole powder metallurgy scope. So from the powders to pressing, sintering, additive manufacturing, metal injection molding, hot static pressing, hard materials, functional materials, and all other accessory studies and endeavors that help producing better parts. We have more than 200 presentations ready to be shown at the conference, and the selection is going on at the moment. And we will have a full program in the early summer or late spring. So please consider joining Glasgow, and if you haven't proposed a paper, you can still join as a participant. Yes, so further activity we do we do a lot, but I want to focus today because we're talking about the green transition here. So I want to focus about what we do for sustainability in EPMA. And when we talk about sustainability and powder metallurgy, there's even a logo which has been used by the fellow friends in America, and we always think it's green because we go to near or even net shape parts without wasting material or wasting very little material compared to other technologies. So, in generally speaking, we are thinking that we have an advantage here. But on the other hand, we run with powders which are, let's say, can be fairly expensive compared to the other raw materials. So it's not given, and the statements about PM being green need a proof. So we already started trying to stimulate projects, and we have asked all our fellow associations, for instance, to start a global harmonized effort on sustainability. As you probably know, and you probably know from the news recently, the not in all areas of the world we have the same sensitivity to this subject. So it's not easy, but we are trying to do that. And to foster to raise the awareness about sustainability, we also introduced what we have called the EPMA Sustainability Award in 2023. And yeah, you can see here that we have had already some winners. In 23, we gave even 3 prizes when we started, and gold, silver, and bronze, but we switched to just 1 in 2024, and we are currently waiting for the finalization of the submissions for this year. So we will see who will win in 2025 and will get the prize at the Congress in Glasgow. And then we do projects that we sometimes we stimulate, sometimes we just take part. This is one example of a project about thermoelectrics, where we plan in the end to recover waste heat. So that's a way to make all the processes more efficient and more sustainable. And in addition to that, we are using waste material, which is actually in mine wastes, in abandoned mines or even running mines, but normally treated as a contaminant, so scrapped. And we can use this tetrahedrite, which is a special material, let's say, to produce thermoelectric devices. We are here just as a dissemination and communication partner, but we are working a lot on this, and you probably have seen some advertisement here and there about this project. The second project I want to show you is actually a project that we will talk about today because it's rescue tool, and there will be the second lecture that is actually a link to this project. It is about the recycling of cutting tools, or anyway hard metals coming from used tools, so that we don't need to actually mine again tungsten and cobalt to produce new tools, and without downgrading the materials, so that we can produce tools and not just use the recovered material to let's say as a filler in other places. So please follow these projects if you're interested. The last project I will show you is Reptis, which is actually another approach. We're talking about titanium here, again another critical raw material like tungsten and cobalt. And we are actually here, we have a Ukrainian company that is mining a mineral called ilmenite in Ukraine, and we will help producing powders with the process that they have developed, and that we will improve and make even more sustainable during the 4 years of the activity. The plan is to have powders that can be used for PM producing parts. So Especially, we start with metal injection molding, but there will be probably the possibility of using the powders for additive manufacturing, as you see there as an example, and maybe also in other technologies. So this is what we do in terms of projects, and sometimes we are just partners. Sometimes, like in the case of these two last projects, we are actually coordinators. And then we work, as I already showed you, in training. And this is a more detailed sketch of what we do for training. So the summer school is definitely the most important event, and I already talked to you about this. Just add as written here that it started in '98, so it's really an established activity. And some of you know it well because some of you are lecturers there or have been there as a trainee. Then during the Congress, we have the Young Engineers Day, and this is just a couple of days during the Congress where students can participate basically for free in those days with a specialized program for them. And they can also join the rest of the Congress with a reduced fee, which is not written there, but I add that. And also, we have restarted in the project the so-called PM for Beginners, which is lectures for newcomers to powder metallurgy, also during the first days of a Congress. And then, of course, in my view, all our seminars and all technical sessions in the Congress are very good for training. You learn really a lot from the technical presentations there. Yeah, details about the summer school in 2025. As I said, we'll be in Lund. A feature here will be also that we will have the possibility of visiting Höganäs, so one of the main producers of metal powders in the world, which is relatively close to Lund. And you can see it in the map at the top. And yes, you can see all the details here, but if you haven't done it, if you are interested, please go to the website and find all the details and apply for that. This webinar will go in a sort of frame that we are starting to make real, where we want to address many different, let's say, targets, and starting from the PM professionals, and this is where we are new or already experienced, and we will probably also use the single lectures later as a, let's say, on-demand training for the people on one of the websites that we use. And then we also have plans to go to lower levels of education, to undergraduates, and even lower levels, and on the other hand, also address specifically the end users and the designers. We already have a global powder metallurgy database, for instance, that is used by many people every year. What about today? I've more or less finished the presentation. I just want to dive into the session today. So we started this series because we want to be more proactive in promoting powder metallurgy in the green transition. We started last year today, as I already said. The plan is to organize at least one session per year. And for the moment, we have this format where we have 3 different topics in each session, but we will keep repetitions really to a minimum. We might repeat maybe the same presentations or slightly improved or updated in the next years, but I don't think it will happen very quickly. You're welcome to take part in all of them, so because they are quite different every year. And we were recording everything, and this will be a sort of playlist finally on our website. So today we have 3 speakers. As I said, we have Benjamin Haller from AM Academy that will tell us about, yeah, sorry for the banner running, sustainability of additive manufacturing. Then we will have Teemu Karuma from Ticomet and the Project Rescue Tool talking about recycling of hard metals. And last but not least, Dirk Zepp from Högeras in on the topic of soft magnetic composites. So 3 different topics, and you probably are coming from different areas now, so maybe you are more interested to one or the other. But I urge you to take notes for every lecture, because there will be the test. Finally, I will give you a link where you will be able to take the test online immediately, and then we will close at 5:30. So I already went over. Um, I will just Well, okay, I just already said that we will have Q&A at the end of which lecture, and you will be able to use the microphone and the camera if you want to pose the question directly. Don't be shy and make questions to our lecturers. The test is 30 multiple choice questions. Some questions you will have to answer in only one answer. Sometimes by answering with the wrong answer among the group, you will see it. Or in some cases, you will have to select more than one option. You will understand. I will give you 20-25 minutes, and maybe we can go a little bit longer if really needed. But I mean, let's try to keep it in this range. We will use SurveyMonkey as a platform. You will get the link when we will start, and you can always contact me when needed if there is any issue. So, and you will get the result when you finish the survey. Then you will get a certificate. So, yeah. Finally, you will get also a feedback certificate, feedback on the webinar, and I will ask you to fill it, all of you, because at the end you will get the link to receive the PDFs of the presentations, and also the possibility of rewatching the video. But we need your feedback, so I hope this is a good bargain, that you need to fill the questionnaire in the next days, and then you will get that in return. We need your feedback to tune the next. Good. So thanks. Enjoy the session. And I will now give the word to the first speaker. We are already 3 minutes late. Sorry for that. And I will then call to the stage Benjamin Haller from IEM Academy. Benjamin, can you switch on your camera and microphone and come to the stage?
Perfect. Now
there he is coming. There he is. Yes. Thanks for being here. You will introduce yourself probably, but in the meantime, if you want to share the slides, and then I will leave you alone on stage to our friends. I see there is a question from Andreas. Andreas, I will probably give you some more information later. Yes, but now I prefer to give room to Benjamin.
Perfect.
Is the screen loading? Yes, I see it. Thank you. I will disappear. Please go on.
Perfect. Thank you very much, Bruno, and pleasure being here. I hope you can all see here. If not, just write something in the chat. Quick introduction at the beginning about myself and about IEM Academy, because I guess most of you have not heard of IEM Academy before. So I'm Benjamin, originally from Germany, but now living in Paris, France here. And I'm working in the AM additive manufacturing industry for around 10 years. During these 10 years, I have worked in quite different positions, and this will also help today to look at this topic of sustainability of additive manufacturing from different angles. Basically, I started working at a machine manufacturer of metal laser powder bed fusion. Worked there a couple of years, then continued working in Sweden for like a part producer and research institute. And then after that, since then, I'm working with material supplier of aluminum powder for additive manufacturing. And more recently, I have co-founded the AM Academy. So what we do at the AM Academy is, as the name suggests, education for additive manufacturing. So helping companies to implement additive manufacturing technologies. What we do here, it's 100% independent of any supplier, also of any technology, so quite broad, focusing on all industries. And the AM Academy was co-founded together with a company called Empower. And this is also going to be important for today, because a lot of the work that I will be presenting is based on their research. So just quickly about Empower, this will be my last slide for the introduction. So Empower, you can see the team here. It's a consulting company that is 100% focused on the additive manufacturing market. It was founded, I believe, about a bit less than 10 years ago. What they do every year is they bring out a market report focused on metal and polymer additive manufacturing. But then they do also quite a lot of research about different technologies. And of course, also about sustainability. And I will today, basically, what I will be presenting is based on research that has been conducted by Empower about sustainability. So today I'm going to talk about 4 key areas. First of all, comes basically 1 and 2, the more technical parts. I will start by giving a background about the different aspects of sustainability calculation for additive manufacturing. Then in the second part, I will talk about sensitivity analysis. So basically talking about the 7, 8 most important input factors and how they influence this calculation. So 1 and 2 is really focused on sustainability during the production of parts itself. Then during step number 3, we basically go 1 level higher and look at the life cycle assessment. So also what happens especially after the production, and then end with a summary. And let's dive right into the sustainability calculation. I will not go into detail about the technologies that we cover here. I hope you all have a basic understanding of the AM technologies. I will mainly focus on 3 technologies that are highlighted in green here. Laser powder bed fusion, directed energy deposition, so also having like a wire technology in comparison, and then metal binder jetting. So even though I will not go and present those technologies in detail, I hope you know them. Just a quick overview about them, maybe for those who know it already, also a little refresher. First up, laser powder bed fusion. You see in the top left a bit functional principle. This, as the name of course suggests, it's a powder-based technology. It works with a laser beam. Conventionally, was more working with 400 watt. Today, what we see in the market is up to 1 kilowatt, and also multiple laser machines. And this we will also talk about in the sustainability calculation, how this will influence the sustainability of this technology. It uses support structures, and then here the typical layer thickness, also this we will talk about the productivity. It's 20 microns to around 100 microns. So for those of you who haven't seen it, this is a melting process of a 4 laser machine here. So much about laser powder bed fusion. The next up is directed energy deposition. This exists also with powders, but for this presentation, we decided to keep wire in here, also as a comparison. Either works with an electric or plasma arc. Yeah, basically not so much more to say about this. I forgot to say this also. Basically, we focus for the materials here on steels, which is available for all three technologies, but then also aluminum and titanium. You will see here a process video. So for those of you who haven't seen the process, I mean, this is now a speed up version of the process slightly, but still this will become important in the sustainability calculation as well. It's a significantly more productive and faster printing process, which then of course also has some impact on the sustainability. And then third process we're going to focus on here is binder jetting. Again, a powder-based technology. This today mainly works with stainless steel. Titanium and especially aluminum is under development here, but especially because of the sintering, this is not really mature yet. And I think this is what will be important here as well is, of course, you will have the printing itself, but then especially for binder jetting for sinter-based technologies, debinding and sintering will be very important. All right, I will jump over the video here and let's dive right into the CO2 calculation. Basically, we will always look from the beginning, material extraction, then feedstock production. So in this case here, wire, and today also focusing on powder here. Then the manufacturing process, and then the finishing itself. We focus on the first three steps here today. Then one level deeper than that, we will go a bit more into detail for the three printing processes. This is particularly important, not only to look at the printing of the parts itself, but looking at the entire process chain. This is what we're going to do now in this chapter. And then mainly in the sensitivity analysis, we will also have a look at some of the most important input parameters here, such as productivity. So what happens if we increase the laser power? What happens if we increase the layer thickness, for example? So let's have a quick look at the material extraction and feedstock production itself. Here, there's of course big differences in the different materials. Of course, if we talk about titanium, for example, especially here during the alloy melting, it's already significantly more energy intense, so it will depend a lot on which type of energy mix are we using. So here we will look at this later also in the sensitivity analysis. We will look at different recycling technologies, which has an impact, of course, again, more for some materials and for others. Then when it comes to powder production, one important factor will always be the powder yield. And this is a big controversy in the industry. When we look at additive manufacturing, for example, for laser powder bed fusion, what we use is typically a particle size from 20 to 60 microns. So now, depending on the powder production process, we have a yield factor in this powder range of around 40, 50%, depending on the technology, would already be very, very good. In some cases, it will be lower. So if we now consider that the yield is only 40% already here during the powder production, there would be much more significant impact on sustainability. So here the question is always, how do we factor this in? Because in reality, of course, we use the non-usable fraction for other processes, either other AM processes like binder jetting that works with a lower PSD fraction, or directed energy deposition, for example, with a higher PSD fraction, or for altogether other processes. But in some cases, especially for aluminum, this is a bit more challenging. So this is already quite important to consider when we talk about sustainability of powder-based technologies. Wire drawing, typically a higher yield, also less energy intensive here, so that's not so much of an issue. Then briefly looking at some of the most important factors here of the powder bed fusion process chain. Again, I want to highlight here some factors. Importantly, here during the printing, the machine utilization will have a very important aspect, important influence. We will show later the impact of printing one part over printing a fully utilized build chamber. What is happening here right now in the printing process, typically the machines are using infrared lasers, which are not so efficient. And here we see new laser sources in development, like a blue laser, green laser, also diode lasers, which will have a higher energy efficiency. So also on the printing process, there's a lot happening. And then for powder bed fusion, but basically for all powder technologies, what has a quite strong impact is the losses that you have both during the printing process, where powders are being stuck, blown into the filter, but then also during sieving, unpacking. And here, this is basically for all additive manufacturing technologies today. Support structures or waste is basically not recycled. This could be done, but it doesn't make sense so much for this very low volume. So typically this is not being done. Then looking at the binder jetting process, what will be here, one of the most important factors is actually the debinding and the sintering. What is the case very often for the binder jetting process is that there's like a small, rather inefficient sintering oven being used. So this will have a very strong impact, both the utilization of this furnace, but then also how much energy is lost during the sintering, how much energy is used to basically reintroduce into the process. And then third here, more simple process chain is the DED process here of the wire arc. Here the printing itself, because it is relatively faster process, has actually not such a high demand for the deposition itself. What is here sometimes more important than the deposition itself is actually all the periphery around the printing. So the robot cell, the weight capacity, the suction of the process. This can have a relatively high energy consumption. And then exactly the energy source used. So here, electric arc has a relatively low impact, plasma, and then laser would have higher CO2 impact. And then we will not talk so much about post-machining, but this, of course, has to be kept in mind that while binder jetting especially produces parts that can often be used as is after sintering. Especially with DED technologies, there will still be a lot of milling and post-processing involved. All right. So let's have a look at some of the most important influencing factors here. What is the basis for this is a tool that we have developed here at Empower, which basically allows us to calculate the carbon footprint of those different technologies and materials. And this approach really allows us to calculate the exact carbon footprint based on all the data that is in there, also for an exact quantity. So very often for those type of sustainability calculations, it's basically average values being taken. But of course, it's a huge difference if we talk about 1 part, 100 parts, or 1,000 parts. So with this tool here, we can basically really simulate different values. So first of all, looking at the production batch size, and basically directed energy deposition, you always produce individual parts, so it doesn't make a difference. But as you can see here on the left side, for laser powder bed fusion, and then for a binder jetting system, relatively large binder jetting system, you basically, when you produce one part, have 3 to over 5 times higher CO2 emissions as compared to when you use a fully utilized build job. And here on the right side, you can basically see how this splits up between the green bar here, which is basically the material, and the dark blue, which is the printing of the part itself. You can see that if you produce a single part in the build job only with powder bed fusion, you have almost twice as high CO2 emissions here in this example as with better utilized. This always depends how well you can actually utilize it. But the reason is both in the material use. So even though the final part will have the same material being used in it, you have more waste, especially during the printing process, because there's always a certain amount of powder that ends up in the filter. So that's why also the green bar here is almost twice as high. And then basically here the blue bar during the printing itself. So important aspect. Then the second one is a bit looking at the alloy group. And this is also important to take away. We have here aluminum versus titanium. But if you would take steel, that would basically be quite similar here to aluminum. So for aluminum parts, when we look at laser powder bed fusion here, the majority of the CO2 emissions really come from the printing process itself, because it is a very slow production method. Here for wire arc DED, it's basically not as extreme. The material is already bigger. But then when we look at titanium, because here the CO2 emissions are much, much higher during the raw material extraction already, the printing itself has a much lower impact. So this makes the optimization of the printing process that we come to later much more important for laser powder bed fusion of aluminum as compared to titanium. If you want to reduce the carbon footprint here, it is much more important to look at the raw material production itself, to use a beneficial energy mix during raw material production, to recycle material. It's of course always important, but much more important here for titanium. Then Another topic is the part design itself. So topology optimization, basically what we look at here, again, for aluminum and titanium is what you saw here is a part that was basically produced for milling. And this is often not optimal for additive manufacturing. That's why it might not be a fair comparison. So you saw here LPBF had roughly twice of the milling. Now milling is basically not changed, but for laser powder bed fusion, we have now only 50% of the volume. And we see already here for the aluminum part, we can basically we get on par. Whereas sand casting in this example is even lower because also here we can basically produce the optimized part for titanium, where if you look back at the example here, we were having higher CO2 impact for the LPBF part here. We are now significantly lower, again, because of the higher share of the raw material here. So especially for titanium, this has a quite big impact that we actually use also parts that have been produced, have been designed also for additive manufacturing. And this we will talk about also in the later stage again. Then looking at the productivity, this of course will also reduce the CO2 impact. Now here we are comparing a standard process, 400 watt laser, 60 micron layer thickness, with a more productive process. So here, of course, in this example, the material remains unchanged, but by basically increasing the layer thickness and the process itself, we can significantly reduce the carbon footprint in this example. So it's simply a more efficient usage of the printing itself. Higher laser power here. Then what we see also, it's not only increasing the layer thickness and making a more strong laser. What we also see in the industry happening right now is different beam profiles. So for example, a ring-shaped beam profile that even more speeds up the process, and then also there leads even with a lower laser power, you can increase the CO2 footprint. Then here looking at the local energy mix, in this example of aluminum alloy. Of course, you can, I mean, here we showed now only for LPBF, what is the impact of where you produce the part. Here we used now the example of average CO2 emissions of China, but you could probably use a lot of different places. Then in this bar here, somehow an EU average, which then already significantly reduces this bar. And then third here, with renewable energies, which then of course almost reduces it to zero. So now if you would use European ingot production, you could even remove this bar here. So you would go down significantly in this bar. So obviously, whenever you talk about CO2 emissions, very important to look at, okay, where is the part actually produced? What is the local energy mix there? Has a high impact in this case. All right. So this was basically, I would say, the basis. Now taking one step back at more of a life cycle assessment. So if we summarize on the left side, what we discussed so far is on a part per part comparison, additive manufacturing it may be more sustainable, but it's highly debatable. I think up until today, as Bruno also mentioned initially, I think it is a lot marketed as a green technology, but I would say the truth is not as easy, and it, as I tried to show a bit here, it depends really on a lot of different factors like material, part design, and also the quantity used. We argue that it's somehow an incomplete approach, because if you take a part that has been produced for conventional technologies and now you are simply trying to produce it with additive manufacturing, you're not using the full potential of additive manufacturing, and that's, so to speak, not really the idea. So what you need to do is really to optimize the part for additive manufacturing. I will show one example, but there's multiple of them. For example, weight reduction, parameter optimization, and then in many cases it will be competitive. So what we need to do is more on the right side, really optimizing parts, and then really look at the complete life cycle of parts. And this is really what additive manufacturing is strong at. Reducing the usage of material, optimizing inventory management. So additive manufacturing, where it really shows strong benefits, is when you produce parts on demand, no minimum order quantities, there's no stock keeping necessary. You can basically have a digital warehouse. You can produce parts locally very easily, and then you can lower the fuel consumption, for example, again, by reducing weight, making parts more efficient. So here again, showing this entire cycle, again, highlighting some of the most important aspects here. First of all, during the manufacturing, the machining volume, not to forget, and I hope I showed this also today, machining is still always important, and is also involved in additive manufacturing. But still, especially for laser powder bed fusion or binder jetting, there's almost no or sometimes no machining involved because of near net shape production. So here you will have much less machining and also much less waste that is needed, so much less material need. As I said already, localized manufacturing, so you could really use the beneficial energy mix, and also have less logistics costs. But then this is where I will show also the example here. The biggest benefit, I would say, that you have with additive manufacturing is in the actual use of the parts. So improving the energy efficiency by, for example, reducing the weight, by making a turbine more efficient, by improving the aerodynamics of a certain component. This is where additive manufacturing is really more sustainable, and where it's probably not debatable anymore if you select the right part. So to show this, I just brought this one comparison of, on the left side, the conventionally produced bracket with milling used in an airplane, and then on the right side, the topology optimized brackets for additive manufacturing. Again, here you will use already much less material. So in this case, AM might be a bit more efficient. But if you now look at the overall lifetime of a plane, and what, for the simple calculation here, what I considered is a 20-year lifetime of an aircraft, and per kilogram of material saved, a value that you find, it's 2,500 liters of kerosene saved. So if you actually reduce this bracket here, as is shown here, you could save up to 43 tons of kerosene over the lifetime of kilogram CO2 over the lifetime of the airplane. Now, is it really 43 tons or more or less? I don't know. But I think this example shows quite well that instead of really arguing, is it really a bit more or a bit less during the production itself, this will bring you the much higher level. And this is, of course, the most obvious example. But there are actually much more examples how additive manufacturing can be used in a sustainable way. Then what can you do as a designer? Of course, this first one here with the airplane example, it was kind of the obvious example, but there are much more. So really use additive manufacturing where it really makes sense. Consider sustainability already in the identification of components, in the part identification, and use it really where it can also have a positive impact on the carbon footprint. Because this, of course, weight reduction, it only works on some components. On many other, it's not beneficial and has no impact. Then second one is design optimization. As said, it doesn't help to simply produce the same parts that were produced for milling, for casting, but the part design really has to be optimized for the function, being it lightweight components, being it improving the efficiency of a turbine or a motor, or also by making parts more durable. For example, a tool that can now last for 20 years and not for 10 years anymore. So the best part is still the part that doesn't need to be produced at all. And then one more aspect that we didn't talk about today, but of course, additive manufacturing technologies, especially directed energy deposition, but also laser powder bed fusion can be used to repair components. And this again has a very positive impact, of course, on sustainability when you don't have to produce the entire component, but you can just repair a part. Then looking at the summary, the most important points, I would say these are the 6 most important topics that will also be quite important for the test later. So number 1, this important, additive manufacturing is so often highlighted as a sustainable technology. And I think especially in the early days, people said, okay, whenever you print a part, it will be beneficial in terms of sustainability. That is not true. It really depends, and especially fully utilized machines, especially casting whenever it makes sense, will exhibit a similar or even smaller CO2 footprint than additive manufacturing. Secondly, reducing the weight of AM part designs. This will have a very positive impact, both in the raw material that you use and then in the material production. Reducing the weight is almost always positive for additive manufacturing. In the case of binder jetting, it's also trying to make the part smaller, that you can fit more parts in the build shop. And this will improve number 2 here, but then also in number 3, reducing the weight, of course, has for many components also in the use a much more positive component. But yeah, this again depends very much on the application, and it should also not always be used as an argument. Then looking at the local energy mix for aluminum and steel parts, the most important aspect of the local energy mix is during the production of the part, whereas for titanium components, this is during the raw material production. For titanium alloys, I think this I mentioned, it's really using renewable energies during the material production. And then recycling rates will, of course, influence very much, especially in the powder production, where we have a very energy-intense melting process. So here, reusing materials that we don't have to extract the ore again will have a positive impact, and especially for additive manufacturing, where the quantities are still very low, this is actually feasible to also reuse materials more than for other technologies. So I hope that this covered some topics that you're interested in, and yeah, I'm happy to answer questions now. So Bruno, giving back the word to you, I guess.
Here I am, coming back on stage. Thanks, Benjamin, for this presentation, and I hope you can hear me.
Yes.
Yes. I will switch now to the discussion mode so that you can be able to open your microphone and camera if you want to pose the question in person. I don't know if Andreas already made posed the question in the chat, if he wants to come on stage and ask it directly, or yes, please. I see other people. Maybe I will read first the question from Andreas. Why not considering the printing powder yield process as a recycling input for following processes? So anything needed to make it usable as recycled material is allocated to the process. The rest taken off, I feel this shall be in line with ISO nomenclatures. Which approach include, exclude, reuse is used in the CO2 comparisons you showed?
Okay, so I hope I understand correct. If not, Andreas, please feel free to use the microphone here. But to our knowledge, in the majority of cases, the losses during the printing itself, they are not recycled. I guess you could technically do it for some very, very expensive materials, like really printing gold, for example, what you are really reusing all the material. But the material that is lost during the printing process, that ends up in the filter of the machine, for example, this is simply not reused because it's technically challenging and would be more expensive. Same for the material that is lost during the depowdering. So you could technically reuse this material, but yeah, as of today, this is not the case. But then for higher quantities, for titanium powder, for example, it could be done. Yeah, but this has not been done.
I see Andreas on screen. Maybe he wants to say something.
Yes, I understand the answer. The second question, basically building on top of this, is when you look at the CO2 data that you have compared of the different processes, which approach has been taken then? So the in theory recycling of the losses or not?
In the printing, it was the losses during printing, they were not recycled in the calculation.
In the numbers that you've shown,
Yeah.
just for me to understand.
Yeah.
So in case of recycling, it will improve.
It will improve, yeah, exactly, and this will again depend on the utilization of the print job. So if you print a single part, it can have a huge impact. I think again this depends now highly on the process parameters, but especially for those large printing machines that are more and more the trend. Let's say if you would print one part in the center of the printer, so you have let's say utilization of the entire printer of maybe 10%. You will blow off so much of the powder into the filter that there's a huge loss. So it might be that even though you print a 1 kilogram part, you will actually use over 3 kilograms of powder that ends up. And also for very complex, let's say, heat exchanger with internal channels, there will be so much powder that is also stuck in the support structures. So this can be significant. But we try to stay realistic. We didn't use that here because, to our knowledge, it is usually not done in the industry today.
Okay, let's try with, I don't know the names because I just see FR on the screen. So please, if you recognize yourself, you can speak. Who is FR? FR should be Francesc Roca, I think. Do you have a question? No? Who has a question? Maybe you came on screen, but you didn't have a question. Tobias? Yeah.
Yeah, I would have a question. Thank you. Thank you for the presentation as well. It's kind of related to the previous questions. I wonder about the powder reuse in powder bed fusion. Is the powder that is left in the build chamber, I'm not talking about what is blown away and in the filters or something, like just the powder that is left in there, do you consider that to be able to be reused that indefinitely, or is there some limitations on how many times you can apply this powder which is left into the hoppers or whatever?
Yeah, in this case here, we consider that we can reuse it indefinitely. And again, this really depends on the application, I guess. You have different studies here that you can reuse it, I don't know, 10, 12 times. Again, this will depend on your utilization. I think you have some extreme cases, like in the medical industry, where you say, okay, you need really virgin powder, but this is typically not the case. So yeah, this we considered that the powder is reusable, which is standard, I would say, in the industry.
But just a ballpark number of how many times can you reuse it in laser powder bed fusion? So not related to the calculation itself. Do you know?
I mean, again, there's different studies, and I mean, if you look, you will always freshen up also with new powder. So if you look at the process, if you keep recycling, let's say after 10 times, there's very, very few left only, and typically you don't have to throw away powder from that unless you have a very, very strict requirements. So yeah, basically this is not a factor here. One effect that you will have over the time is that your particle size distribution will change, sometimes even to the better. Basically, by sieving the powder multiple times, you will sieve out more of the very fine particles. So it has an effect, but in this case, not necessarily a negative effect.
All right, thank you.
I will take only one more question, sorry. I will go to Sophie, I guess. Sophie, is it you? I see SR on screen.
Yes, it is me. I don't.
Hello. Yes.
Hello, can you hear me? Yes.
Yes. Yes.
Yeah, I don't have a real specific question, but if you give me the opportunity to do it, maybe I will ask. Does your sustainability tool can be also applied for near-net processes? And because in fact I'm also interested to compare near-net process to other processes, and especially on the powder production compared to classical casting or so. My question would be, you show a very nice kind of table with all the calculation parts from powder production to the process. Can this tool be used for near-net process or conventional PM, I would say?
This today we don't have in the tool yet. No.
Okay.
We have milling and casting basically as the tool. Conventional technologies. Simply also, this is not our expertise, so to say. So this we don't have in there.
Okay. Thank you.
So thanks, Benjamin. I have to stop here because we're running a bit late, maybe. But if you have other questions, can you type them in the chat? Maybe Benjamin can address them in the chat.
I will do that. Yeah.
It's okay. So I switch again to the presentation mode. So this will kill all the other microphones. And yeah, we have to switch now back to the lectures. And I will call on stage Teemu Karuma, who is the second lecturer for today. There he is.
You see me and can
Yes.
hear me? Okay.
Yes, good. Definitely. Yes. If you want to share your slides,
Yes.
you're free to do it. And as I already said, he is from Ticomet and from the Rescue Tool project. He will introduce himself and then he will explain what is happening with the recycling of hard metals. Yeah, let's start the presentation. Do you get, yeah, that's presenter mode.
Okay.
Last change, and then it will be fine.
Yes.
Great. Thank you, Teemu, and I leave the floor to you.
Thank you, and good afternoon also from my side, and warm welcome to this webinar, PM in Green Transition. My name is Teemu Karhuma. I come from Ticomet in Finland. I work in R&D here. And besides to Ticomet, I also work quite a bit with colleagues in Plance and Ceratizit, to which Ticomet belongs to. So Plance and Ceratizit, they are one of the world leading companies in tungsten and molybdenum refining and production. Ceratizit in the area of hard metal tools. So practically we supply raw materials to Ceratizit, our sister company, and then Plance is then a even bigger corporation in production of various parts to metallic tungsten and metallic molybdenum businesses. So let me start with the contents of my presentation. First, in the first slide, I would like to give you a very short introduction what hard metal is. Then a motivation why the recycling and the green transition is very important topic indeed. Then very short introduction to EU project Rescue Tool, which was already mentioned a couple of times here. And then the topic itself, tungsten recycling market, tungsten-based secondary raw materials, recycling processes. And then at the end of my presentation, I will talk a little bit about general trends influencing the hard metal recycling and industry in general when we think about green transition. So what is the time? It's 1:45. Yeah, I just check that I will try to keep my time. Hard metal is a composite material of tungsten carbide and cobalt. You see here on the right side in the picture, the gray particles there, which are tungsten carbide grains, which are bonded together with a metallic cobalt binder. And this concrete kind of material, which consists hard tungsten carbide particles, which give the wear resistance and hardness to the material, and cobalt gives nice toughness. And the combination of hardness and toughness in case of hard metal is kind of unique and hard to replace in many applications, which you can see on the left side of this slide, some cold forming tools, metal cutting inserts, and saw tips for wood and metal cutting, and then rock or concrete drilling tools. So many applications where very strong materials are required with good combination of toughness and hardness. And then a quick quick introduction to a typical flow chart of hard metal production. We start with raw material procurement and in the tungsten carbide and cobalt, and then other elements which are sometimes needed are mixed and milled in a grit or a ball mill. The slurry is granulated or dried and granulated to free-flowing powder. Then there are typically quality control step in this phase. The powder is compacted to give a shape and can be green machined afterwards. And the very important step for hard metal production is the sintering, as it's for any kind of powder metallurgical processes, where the hard metal gets the final strength and properties. And then afterwards, there is again a quality control step to check the porosity, microstructure, carbon balance, etc. And then at the end, there might be some post-treatments like coating, grinding, joining, welding, brazing, etc., etc. And in my presentation, I don't cover the recycling, which might be done within this process chain. So sometimes, or in many cases, some filter dusts are created during the spray drying of the slurry, hard metal slurry, and these powders are recycled back to the wet milling step. Or from green machining, you create powder which can be also put to the wet milling step. This recycling within this hard metal production chain I don't cover in my presentation, but only the parts which are used, they are produced and they are used in the final application, like metal cutting inserts. They are used, they are worn, and then they are recycled back to raw material. And these recycling processes I try to cover in my presentation. And then I come to the part of motivation. I took a couple of slides from NASA climate change studies and videos. We see really now in the last years that the climate is changing. And that means we see really temperatures above if we compare the temperatures to before industrialized times. For example, here 1994, 1998, we see only a very slight temperature increase. But if we go to the last years, we already see a huge above and close to 2 degrees C temperature increase in many areas in Europe, in Asia, and especially in the northern areas in the world. And it's not only the temperature that matters. There are also studies projecting that the wet pulp temperature, so that means temperature at 100% humidity, these conditions can become reality in many places in the world. And in this case, this is a map with 2.5% global warming and days above 28 degrees C wet pulp, so 100% moisture at 28 degrees C temperature. The probability of having such days is very high in many areas where there are a lot of people living. And this picture draws the attention. It will be difficult to live in such areas. It's not lethal, but it's very hard to work in such condition. And it's not only the temperature, but also drought. And we see in this map likelihood for year plus drought in the same scenario of 2.5% global warming. We can see that there are many areas. The reddish color indicates already 50+% likelihood for year plus drought. And there are areas, Australia is almost full of heavy risk for drought, also Spain in Europe, and parts of France, which have almost 100% likelihood for year plus drought. And also big areas in Russia, Ukraine, where a lot of food production takes place. So it really matters. this topic is very, very important. If we talk about hard metals, the production of hard metal is quite environmentally burdening. There are studies showing figures like this, that if 1 kilo of sintered hard metal is produced, and there are scenarios of zero recycling and completely recycling, the energy demand is very high. The landfill, if you make from concentrates hard metal, it's extremely high because tungsten is in the earth crust. It's in the very low quantities. So in typical mine of tungsten, there can be only like 0.3% or 0.5% of tungsten in the ore, and you create huge amounts of waste when you beneficiate tungsten from these mines. And also other indicators, acidification, eutrophication, and water depletion. The recycling plays a big role here. And we published in the last Planche seminar on the right side the figure, what is the CO2 emissions for production of 1 kilo, in this case raw material, tungsten carbide. And there are articles available in the internet that according to one study, Chinese tungsten carbide production with mainly coal-fired electricity production, the tungsten carbide and 90% from virgin raw material, it can be as high as 60 kilos of CO2 equivalent per kilo tungsten carbide powder. And in our sister company in the US, which is mainly running based on the scrap raw materials, chemical recycling, for them the figure was for 2018, it was 12 kilos of CO2 equivalent per kilo tungsten carbide powder, which is still very high. And then for Ticomet, which is running 100% zinc recycling from green electricity, the CO2 emissions are close to zero. So we really need to think about the sustainability of hard metal production with this background. And it's not only environment that benefits from recycling. Tungsten is a strategic raw material, is classified as a critical raw material, both tungsten and cobalt, by European Union because of the economical importance and because of the supply risk. And the supply risk comes from the fact that most of the tungsten is mined in China, and even more tungsten is produced in China. So there are resources outside of China, but the virgin tungsten is up to 80 to 90% produced in China. And in the rescue tool project, we are trying with partners from Europe, and the partners are all the companies or companies from hard metal industry, so from scrap collection to recycling to hard metal production and research institutes. We are trying to create a closed loop recycling scheme so that as little hard metal tools would be lost as possible and they could be recycled as good as possible. And this would be done, or we are trying to do this so that as currently hard metal scrap is collected and sorted according to the application. So the manual sorting at scrap collection facilities, they are the manual labor knows that okay, this part is a metal cutting inserts like in the picture in the center, or then they recognize this is hard metal drill or end mill, and they put these to their buckets, different buckets. But then of course we know that there are different substrates in the metal cutting inserts. They consist of different elements, not only tungsten carbide and cobalt, but there are differences in tungsten carbide grain size, and there are other elements sometimes. So our current idea in the Rescue Tool project is to create a standard in Europe and hopefully even further expanded it, that the hard metals would contain a data matrix code, and the code would contain information what is the tungsten carbide grain size and what is the chemical composition in this hard metal tool, so that it could be recycled as easy as possible without losing any critical raw materials. Then we come to a tungsten recycling market. This is a study from ITIA, so International Tungsten Industry Association, from 2019, when they found out that the global tungsten production volume is something like 108,000 tons per year. And for this quantity, only 35% of tungsten comes from recycling. So it's really a shame that only 35% of tungsten is recycled. And we can see in this graph that the losses, so the 65% or something like that, goes to the losses, dissipation, dilution, and discard. So really high quantities are lost from the global tungsten industry and supply chain. Out of this 108,000 tons, about 65% goes to tungsten carbide products. So the rest is tungsten-containing steels and superalloys and tungsten heavy alloys, etc. And for the tungsten carbide, so hard metal tools, the recycling rate globally is about 46%. And in Europe, I don't have a figure in my mind, but I would say it's much higher. It would be 50 to 60%. But we need really still virgin tungsten into the supply chain, because there are let's say, for example, during the drilling of rock in the mines, the hard metal parts really wear. There are, and then we lose some tungsten in steel. Let's say lose, it's incorrect word, but that is diluted in the steel, and if the tungsten containing steel goes for the next round for non-tungsten containing steel, this tungsten is lost from the loop. And when we look at the tungsten recycling market, also according to the International Tungsten Industry Association, from the first use industries, wear parts is by far the biggest consumer of tungsten. Globally, almost 40,000 tons of tungsten goes to wear parts, and only 15% of that is recycled, about 5,000 tons per year. The cutting tools, so drills and end mills and indexable inserts, is the second biggest first use industry, about 30,000 tons per year. And for them, the recycling rate is much, much higher, about 70%. And for the rest, mill products, meaning tungsten, pure metallic tungsten products or tungsten heavy alloys, the recycling rate is very low. And for high-speed steel, it's a little bit higher, but in general, cutting tools, as we can see in the picture on the right, when all these scrap collected globally, 34.5 thousand tons. Out of that, cutting tools covers more than 60%. So in the wear parts, there is huge room for improvement in terms of recycling. If you look at the hard metal scraps, different types of hard metal scraps that can be recycled, we see here typical indexable inserts, metal cutting inserts, different kinds of hot rolling tools, EDM blocks, mining buttons from drilling of rock, cold forming tools, metal drawing dies, round tools like drills and end mills, and this spectrum is very wide, and the sorting plays a key role there, and this is what we are trying to improve in the rescue tool project. Another cluster of scrap types that plays a big role is the soft scrap, so-called soft scrap, which means all kind of tungsten-containing materials which are not sintered. So powders from filters, floor sweepings, chips, sludges, or grinding liquids which contain tungsten can be recycled, and they are recycled a lot. It should not be lost from the cycle. Then I come to the next part of my presentation. What are the processes that are used for tungsten carbide hard metal recycling? And first of all, I would like to give you a quick sketch how the loop works. So in the process of tool design, the recycling should be taken already into account, so that the attachment also, again, for example, to steel, should be made so that the hard metal part can be afterwards separated and recycled, etc., etc. Tool is produced, it's used, and it becomes to end of life stage, after which it can go to discard. Some hard metal scrap, sintered hard metal scrap, goes to steel melt, because in some cases, depending on the ferrotungsten price, steel melting shops sometimes buy hard metal scrap as a tungsten source, for example, to high-speed steel production. And then the real recycling scenarios, first of all, of course, the reuse. If the hard metal tool is reconditioned, like ground, resharpened, recoated, in this case, this is the most sustainable way of using hard metal scrap. The cycle is very short. There are minimal amount of emissions regarding that. Maybe the transportation is the biggest contributor in terms of CO2 emissions when we consider reuse, but this is anyway by far the most environmentally friendly to use hard metal scrap. Then some part goes to crushing, and majority of this crushed hard metal goes to hard facing applications. So nice wear protection and wear properties of hard metal is utilized, so that some steel parts are coated with crushed hard metal to prevent wear. Then there are companies doing leaching, so that means cobalt binder from the hard metal scrap is removed by acids, and the remaining tungsten carbide is returned to the tool production, and the leached cobalt can be used as a raw material for different kind of cobalt chemicals production. Then the two main processes for hard metal scrap are the zinc processing and chemical recycling, and about them I will give a couple of more details later. First of all, the leaching. So these solid hard metal scrap parts can be put into a dissolution tank with some types of acids, either strong or weak acids, as long as the acid is enough to dissolve the cobalt binder. But as if you consider hard metal having the space between tungsten carbide grains can be only a couple of microns, the diffusion routes for the acids is not very much, and that leads to a long processing times. And also, depending on the acids, the tungsten carbide, remaining tungsten carbide can be oxidized, and that can cause challenges in further utilization of tungsten carbide from this process. Coatings, in terms of, in case of metal cutting inserts, for example, they can cause challenges. And if there are different kind of binder systems like nickel and iron binders, or strong dopants, doping levels, for example, chromium molybdenum, they can complicate the required chemistry. And then we come to zinc processing. This is a picture from our production furnace at Ticomet. So the zinc processing can handle only sintered hard metal scrap, and the hard metal scrap is put together with the liquid zinc, molten zinc, to a graphite crucible, where the zinc alloys with the cobalt binder and cause expansion, volume increase. And after distillation, evaporation of the zinc, the scrap part can look like this in the middle, and this is very fragile and easy to grind to powder. And if we look at a little bit more in details the process, this similar microstructure of a mining tool in the left side can become something like this in the middle when the zinc is alloyed with it, with the cobalt binder. So the tungsten carbide grains are pulled further from each other. And once the zinc is removed from here, from this phase of cobalt and zinc, the leaving zinc leaves empty space between the tungsten carbide grains. So in the final part, there are tungsten carbide grains loosely touching each other, and some cobalt particles in between. And this can be easily ground to powder. The temperature curve and pressure curve could be something like this. We increase the temperature under nitrogen atmosphere, let the zinc react with the cobalt binder. Then we increase the temperature, decrease the pressure, so that the zinc starts to boil and evaporate, and then it's recovered and condensed in the second batch, so that we lose as little zinc as possible. And in terms of powder after the recycling, it can look something like this. In the picture above is the powder after zinc recycling. So there are agglomerates, loose agglomerates, which contain tungsten carbide and cobalt. So the zinc recycling does not purify anything. All the impurities that are in the scrap will be in the powder afterwards, as well as the tungsten carbide grains, so it does not change. So in this case, this is submicron material consisting of tungsten carbide grains and cobalt here, and this powder can be fed then directly to the attritone milling step in the RTP production for the hard metal supply chain, and can replace virgin tungsten carbide and cobalt. If you look at the little bit coarser grains, tungsten carbide grain size powder, the powder is not that much agglomerated after recycling, but there are more single tungsten carbide grains and then cobalt here and there. If we look at the chemical recycling, the picture comes much more complicated. So hard metal scrap or tungsten scrap that goes to chemical recycling needs two kind of different types of processes. Firstly, hydrometallurgical process to purify the materials, and then pyrometallurgical processes to define the grain size of the material, plus create tungsten carbide from the tungsten oxides or ammonium paratungstate. That was the outcome of the hydrometallurgical processes. So there are multiple dissolution, purification, filtration steps. It's very complicated chemistry, and then pyrometallurgy requires very much energy because the material is heated multiple times to very high temperatures. But the chemical recycling is the only option to recycle, for example, soft scrap and sludges or other impure or contaminated hard metal scrap or tungsten scraps. And also the same process applies also for the concentrates. So in principle, hard metals and tungsten scrap can be fed to the APT plants, which produce materials, tungsten carbide from concentrates as well. And here is the process chain for chemical recycling. So first of all the tungsten has to be oxidized. In this case, this is more or less the process chain of our sister company in GTP Towanda. There is a sodium hydroxide digestion, and then out of this digestion and dissolved tungsten, there are multiple purification steps, different steps for different elements. And at the end of the hydrometallurgical process, there is a solvent extraction to change from sodium to ammonium, and then at the end of that, crystallization to ammonium paratungstate, solid crystalline material. And out of that, tungsten carbide is produced first by calcining this APT to tungsten oxides, reduced to tungsten metal, and then carburized to tungsten carbide. And then at the end, there are some milling and sieving steps depending on the producer and depending on the grade that is produced. So multiple times to high temperatures, creating a lot of high amount of energy required, and complicated processes and complicated chemistry. And then coming towards the end of my presentation, general trends that influence hard metal recycling. If we look at, for example, the energy demand to produce hard metal, if in this case the left bar represents tungsten carbide cobalt hard metal produced from raw materials from mines in the North America, the energy demand can be as high as something like 430 megajoules per 1 kilo of hard metal. If the hard metal is completely recycled, and in this case, this scenario is 50% zinc recycling, 50% chemical recycling, but non-virgin raw materials are used, the energy demand drops to around 300 megajoules. And if the material is, or the raw material is only from the zinc recycling, the energy demand drops to around 150 megajoules. So energy is a big contributor, as well as the raw material, whether it's coming from scrap or from virgin sources. It plays a big role in the environmental impact of the hard metal produced. And as we all know, electrification is very important for all of us in any industry. But for that, we need green electricity to make it more green. And but green electricity can be volatile in terms of price. I come to that in my next slide. And we see now, unfortunately, in the last couple of years, increasing demand of tungsten in defense industry, and that might increase the prices. And luckily, we have seen a higher utilization of scrap as raw material, but there is a lot of room to improve that further. And of course, whenever the prices get higher, there is more incentive for companies to collect and recover more used tools and recycle them. But we should make sure that the labor shortage that we face in the Western countries does not prevent us to do this. And this is something that we try to tackle in the rescue tool project to automatize the sorting processes, so that this would not hinder us to further utilize this scrap in hard metal recycling. And as I told, I would like to one more thing about electricity. I'm from Finland, and we have a special situation in the electricity production that we have a decent share of nuclear power as well as wind power. And nuclear power being very difficult to adjust the production, and wind power is very volatile in terms of production capacity. The picture becomes quite difficult. And now we know from the studies that the production costs for the photovoltaic and onshore wind-based electricity is quickly becoming the cheapest option to produce electricity. So that means the production capacity will increase rapidly. And this leading to situation that electricity price is very volatile. We need to really consider this fact when we develop the processes further, that we have to be able to stay flexible and stay flexible in terms of processing capacities and cycle times, so that when we know there is less electricity production, we could run less, and when the prices are very cheap, can be even negative. Finland was last year the country that had the most amount of negative electricity prices in Europe because of high amount of wind power. So the electricity can be really cheap for a certain amount of time, but it can be very, very expensive for other times. And we need to stay flexible when we think about our processing capabilities. Let me come to conclude my presentation. We think that recycling of tungsten and hard metal will increase in the future due to several reasons, especially because of the environmental reasons and CO2 emissions, and also from the strategic reasons. While China produces majority of the virgin tungsten, and we need to stay independent from China in Europe, but also the recycled materials should not be more expensive, but more rather cheaper, so that the market adopts the recycled raw materials. And we think there will be development in the recycling processes going forward, and the scrap collection efforts will be increased. And more importantly, as that was already mentioned in the previous presentation, if we can avoid consumption, this is the most sustainable way. And in case of hard metals, reuse, recondition is the most sustainable way of utilizing produced hard metals. But then if that's not possible, then as much as possible should be recycled. Okay, thank you very much for your attention. I'm open for your questions.
Right. Yes, I'm back. Thanks, Teemu. I think we are quite on time now. Thanks for your lecture. I don't know if people have questions now for you. If Yeah, I see something coming from the chat from Monica Campos. I will read. She has issues with the voice. What is the reason for such a low recycling rate of wear parts?
Yeah, this is a good question. According to our understanding, it becomes from the fact that in many cases wear parts are attached to steel and can be in a large steel part. Only very small amount of hard metal is attached, either as in a mining drill bit. There is a small amount of tungsten studs which do the actual work, and the efforts to remove or separate these hard metal parts from the steel part can be considered as a waste of time or money, and the whole steel part can be dumped into the steel melt, and this can utilize also the tungsten contained. But also there are processes like welding, where hard metal can be welded to steel parts, and then the separation becomes very, very complicated. And of course, where the materials is lost is one contributor there.
And I think also for cutting tools, maybe the difference could be between the mining tools, where probably there is more steel, big parts with just drilling bits at the top, and the normal cutting tools used in the job shops, where you probably have most of them are just solid hard metal.
Yes.
And I think in this case, you mentioned the designing for recycling, and we are probably in a good niche where the cutting tools are actually relatively easy to recycle, compared also, I don't know, to magnets in cars, or where you have to extract the magnet from inside an engine, right?
Right.
I see another question from Subham. I don't know if he wants to say it personally, but I can read it. Our company trades 250 metric tons approximately annually. We would like to discuss the... Okay. you will have to discuss about business there. It's not really a question, I would say. But I see Tobias on screen.
Yes, so I'm interested. Is there any risk of zinc contamination after the zinc processing?
For the zinc process, the zinc can be evaporated very, very well away. So there is only something like 10 to 20 ppm of zinc remaining in the powder after the process. So the zinc being low melting, low evaporating material, it can be evaporated very well. And
okay, so dissolution in the tungsten carbide is also no issue then, or no real issue.
Sorry, tungsten.
So there's the solubility in tungsten carbide for zinc is then pretty low.
No, that's not taking place. The zinc dissolves only into cobalt phase.
All right, cool. Thank you.
Good. Any other questions? I see you have to discuss this soon. But maybe another comment I have. Also in the project, we are going to use another recycling route. I don't know if you want to say something about the bio-derived recycling that we will use in rescue tool.
Yes. Another process that is investigated in the rescue tool is a bio-based leaching. So the Films and Unica in Italy, they are investigating a process to dissolve the binder by organic acids, and the organic acids would be developed and created from the agro-based wastes, so as environmentally friendly as possible. But I didn't mention this because it's not industrially utilized yet. So
sure.
It's under development in the rescue tool project.
We hope to make it
one
here.
option. Yes. Right.
I see also a question from Anthony. How can we improve the recycling process for soft scrap and sludge?
Yeah, soft scrap and sludge are a little bit difficult because already from the beginning, the transportation of these materials are challenging because they are considered as a hazardous waste, and even non-hazardous wastes. For non-hazardous wastes, there are a lot of transport regulation. And now that the material is hazardous and can be contained liquid and solid, they are quite difficult to transport if you really take closer look in all the regulations. There, rescue is also playing some big nice role. We try to lobby in the Europe that the tungsten scraps and wastes should not be considered as a waste. So they should be considered as a raw materials, and these limitations in the transportation should be limited to make the recycling better. But in terms of improving recycling processes, yeah, I would say some kind of chemical recycling is required anyway. And these processes, it's another presentation how they can be developed.
Maybe concerning the recycling and the regulations, we can also say that we just heard that there will be a Circular Economy Act, probably by the end of 26. We hope that it will answer all our prayers, and there will be rules that will, let's say, give a boost to the recycling of the critical raw materials. Really,
right.
Just learned yesterday.
Yeah, this is very interesting indeed.
Let's hope.
Right.
We will push. Okay. I think I don't see any other questions. So I will thank you again, Teemu, and we move to the next lecture.
Thank you.
Thank you. If there are any more questions, please post them in the chat and we will cover them. Thank you. So I call to the stage the third lecturer for today, who is Dirk Zepp from Höganäs. And I hope he can switch on his camera and microphone and come up here with me while I switch back to the standard situation where the attendees cannot switch on the microphone and camera. I'm trying to bring Dirk to the stage myself, let's say. There he is.
Can you see me now?
Yes, we do. We hear you.
Okay, thank you.
So if you want to share your slides, then you will be able to talk about your topic, which is the soft magnetic composites.
Okay, I will try to do that.
Dirk van Höganäs, who actually is one of the main producers of these materials. So he will be, he's totally qualified to talk about this for you.
Do you see my screen?
Still loading.
I'm trying to get my. Let me know if you have it as a full screen.
Not yet. Still loading.
Okay.
Let's see if we have it quickly. Otherwise, we have a plan B.
Yeah, or last time also I needed to do it a second time. Yeah. Is it coming?
No, not yet. Can you try again?
Okay, of course.
Sorry, guys, for this.
Let me try this once again. Cancel. Okay.
Otherwise, I can
now hold a second.
Surely. Surely share from my side in case if it doesn't work. Still loading. Okay. Now it should come. I see. Yeah, I see your screen, and then if you start the presentation, that's full screen. You can just remove the bar if you can hide that, and that's free. Great. So the floor is yours, and see you later.
Thank you very much. So, hello all together. I hope you're still awake, and as it has been already quite a long time with the other very interesting other two sessions. My name is Dirk Zepp. I'm the business development manager at Höganäs, responsible for SMC material, especially in Europe. And just as generic background information, If you're not aware of it, Höganäs produces about 500,000 tons of iron powder materials in different grades per year. And until now, a rather small segment of this business actually was the soft magnetic composite parts of the SMC business. But since around summer last year, with a kind of reorganization, we have now a division called EMM, electromagnetic material. And we, of course, focused mainly on the electrification and the future business of the Höganäs Group. So I will just separate my time here in 3 sections. The SMC material itself, we as Höganäs call it Sommerloy, and I think some of you are already aware of that. Then the LCA of SMC material in general, with 2 or 3 examples from our side, as well as then the production process of SMC material, as this, of course, differentiates from the normal PM business. The material itself, SMC, SMC stands for soft magnetic composite, and the material itself is manufactured and produced by creating a pure iron-based powder material with no other ingredients, just the pure iron, then a very specific coating which is around each particle as an insulation with a very small amount, just of a few micrometers. And this is what we produce in our facilities, the base material in Sweden, and which is quite important. We come to that later on in the LCA phase. And then we sell this in big packs to our direct customers, which are then the compaction companies, which then produce the final products accordingly with compaction tools and heat treatment. And then, of course, the end customer is assembling it and using it for the final application. Quite important, what we always need to explain, especially for customers that are not used to work with this kind of material. And I have to mention here that Höganäs, of course, from the original process is, of course, more or less just a raw material supplier. So we should be actually the last one in the supply chain that is impacted in new designs and in new applications. But in fact, Höganäs learned this over the last few years, that we have to go around the supply chain and that we need to educate and guide designers how to design components and parts which can be made out of SMC material, because some of the designers are not aware what they need to respect during their design. And also, very often, of course, we learn that the difference between PM material and SMC material is not so well known on the design level of the components. Of course, sinter companies that use our material directly, they're aware of this. But when you then follow up to the top of the supply chain, this knowledge, unfortunately, has not yet gone through all the different levels. So on the middle size page here, you see the gas atomized, as we call it normally, bolts. That is what you see, of course, as normal sinter PM material. But this is for SMC material absolutely the wrong shape. We don't use that. What we need is the water atomized particles with a very obscure surface, because this surface is absolutely needed during the compaction process, as these parts after the compaction and with then the low temperature heat treatment will still only mechanically hold to each other. They don't melt together. And below you see this very nice example of 2 particles with the insulation coating in this brown color. And this insulation coating, of course, is extremely important, because this avoids any shortcuts and losses of the particles to each other. These insulation layer should never be damaged or destroyed, neither through the manufacturing process nor to the application used during lifetime. For the heat treatment, as I said earlier already, there are different SMC material grades on the market available, and the heat treatment is normally between 500 and 600 degrees C. So this is far below the normal temperature that is used for sinter components. But for this material absolutely needed. And also the material itself is normally produced and sold to the compaction companies in a production ready status. So the lubrication that is needed for the filling of the material into the tools, the compaction tools, the dies, as well as the ejection, is already in the ready to be sold material. So nothing should be added to the powder material. It is just the powder in the big packs that is delivered. And just again, a short overview. Normally, sintered iron is just a block of iron where you have, of course, a rather high loss level. I mean, if you try to use this for any electromagnetic application, you just have an induction heater system, more or less. And this is, of course, not what you want to have if you design and want to use an electric motor. Laminated steel is the very common standard material that is used today in, I would say, more than 95% of all the electric motors that are in production today, and especially in the automotive business. But laminated steel has certain limitations, and this is because of the sheets that are stamped and then stacked and welded. By that, you have a two-dimensional layer level, and you have limitations because each layer with the surface coating between the different layers is, of course, a border that is actually hurting the losses and the design. SMC components itself, as they are compacted together and still stay single during the compaction process and the heat treatment afterwards, are still able to be orientated, electromagnetically orientated in each direction, single-wise. So by that, actually, you can have the layout in 3 dimensions, and this also has to be respected during simulation, which is a little bit an impact and a challenge for some designers, because the simulation work needs to be with a software that is capable to run on 3D. The 3D is mentioned here as well on this page. It gives you huge benefits on one side, that you are able to design a component which is smaller, more compact. We see on some applications, and this is not our own internal investigation, this is what some companies that are developing electric motors have found out, that on some applications they can reduce the size and the weight of an electric motor by more than 30%, just by using 3-dimensional material and designing different, let's say, motor topologies than with SMC material. The LCA, and we learned today already quite a lot what LCA means and what LCA is about. But on SMC material, of course, we have a certain challenge. And you see here some pictures actually coming out of our facilities. So to produce iron powder and also SMC material is, of course, a high energy consuming production. So we have our own iron melting facilities in Sweden, and these, of course, need a lot of energy, and they, of course, on the other side, produce a high level of CO2. One way to reduce this amount actually is something that we are doing since many years already. So a high amount of the SMC product that we are producing is made out of recycled material. Our recycling level of the material is already today over 80%. So we have only below 20% of virgin iron that we are using in our facilities today. And the energy that we are using today already comes on a high level from green renewable energy, wind and solar energy, as well as water energy. But the target is, of course, to increase this as well. On some of our furnaces to dry the material during the manufacturing process, we are also in process to change the gas that we are using today into biological gas, so that it's also a kind of renewable energy. The LCA cycle for such materials is not only depending, of course, to us. We have to see the full cycle. So here you see nicely on the left side the Höganäs section, which is just on the top, the material that we use and our own manufacturing. Then, of course, you have our direct customers that use their own process and their own energy level to use the material and to create and manufacture the customized product shapes and components. And then you have the full life cycle, which is then the use of the final product during its lifetime, and then the recycling at the end, with the target, of course, a high content of this recycled product at the end also might be returned to us to use the material again. And one of the beauties of SMC material is that once the components are, let's say, at least half open and accessible, you can crunch SMC components rather easily just by forcing it with a mechanical strength so that the component cracks, and then you can collect the SMC material out and return it for the melting process. For laminated steel, as a comparison, which is our main competitor material on the market, of course, the recycling is a little bit more complicated. There is a very clear plan for us, but not only for us, in general, for companies that are using this kind of method to get a CO2 neutral supply chain and base. The plan is to be fully CO2 neutral by 2037 with different scopes. Of course, to reduce the fossil coke and fuels that we are using. And then, of course, using the electricity that is available also as renewable energy, and use other materials which are also low carbon. And this kind of graphic and the scopes might already be aware to most of you. Just for you as a nice overview, which is also giving you some numbers here about the different scopes, how big the reduction impact is. On fuels and raw materials, we have quite a nice section of 11 and 22%. The energy actually is at the moment by 2024, which is the end of last year, in the moment at nearly zero. The reason is that we already, since many years, of course, buying the energy, the direct electric energy, from a high amount of green energy, because our biggest and our largest manufacturing sites to produce the core material is in Sweden, and Sweden, with a high amount of green energy, is of course their very good ground. It would be different if we would be located in the other countries in the world. Transportation and sourcing materials is of course the other side, and as I mentioned already, we are already above 80% of recycled material. But on the other side, we are trying to improve this. So we have a certain target within the next 4 years, 5 years, to get it at least to above 95% of raw material. And you see at the bottom that we have a total of 620,000 tons of CO2 that is already in the process to be reduced, but we still have a way to go. And once again, here a small overview of what the different levels is from the water optimization, the annealing, of course, to get the SMC material production ready. It all has a certain impact on the CO2 level. But with the activities that we have been doing over the last 2 years already, and this is not only for us, we see the same level from some of our competitors, there is the possibility, and it has been tested also from external auditors, that there, at the moment at least, we are able to produce 1 ton of SMC material with a CO2 content of about 0.8 tons. And this is, of course, compared to some of the competition materials, especially laminated steel, about 3 times lower than what they have. The reason is mainly the high content of scrap that we're using and the green energy. And another nice comparison of a design, and you see on the top the reference part, which is a typical state of an electric motor machine. And if you take the full SMC component as a reference and then compare it with the different design levels, which might be considered by certain design companies to use either an SMC part that is splitted because of some design features, or they use a hybrid design, which means a certain content of SMC material plus laminated steel. on different grades, like a GO20 material and NO35. So they laminated steel with the thickness of 0.2 millimeters, 0.35 millimeters, or even with extremely high performing NO20 material, which is very thin but high performance level. But you see that the content of the CO2 is increasing dramatically. And this is mainly because of the different ways of the manufacturing. The numbers were made by an external software that is using base information from the different suppliers of the different materials, and we can rely on this quite securely. These are public domain numbers, more or less. The production process of SMC material, as I mentioned earlier already, is that normally the SMC material is supplied in the big packs of 1 ton of material. Then our direct customers use this material for the compaction and afterwards for the heat treatment. The components that come out of the heat treatment are, after a quality check, of course, should then be assembly ready. And that is a quite important message, that we still need to educate nearly all the designers of companies that are designing components with this material, that these parts that come out of the heat treatment should not be machined. There should be no additional operation. Unfortunately, most of the designers are used to consider additional mechanical operations afterwards, because they come either from the PM materials, so normal sinter parts, or from full metal components, and they don't see at the beginning the need to have an assembly ready design available, because otherwise any kind of mechanical operation which damage or destroy the insulation coating that we are putting during the annealing process on each particle. And unfortunately, this insulation coating is exactly the magic of the SMC material. Just one short example, especially for the ones of you that are not so much, let's say, on a daily level involved with SMC heat treatment. As I said earlier, we have a production-ready material. So there are certain specific heat curves for the furnaces. And at the first step, after heating up to around 450 degrees, we have a certain stable time frame where the burn off of the lubrication has to take place. So the lubrication that has been added to the material up front to be a production ready material needs to be out of the product fully. There should be nothing of the lubrication left in it. And then there is a heat up phase. During this additional heat up phase, normally there is a kind of add-on inside of the atmosphere of the furnace, either with nitrogen or with steam, depending on the different SMC materials that are used for the final product. And so each of the different product groups have a certain additional add-on during the heating process. The maximum period, as you see at the top, between 2 and 10 minutes, is actually related to the design of the final product. The bigger, the heavier, the more, let's say, solid the product is, of course, the more time is needed for the top temperature and then the cooling down. And more or less finally, and I think I'm even quite fast today with my presentation, I apologize for that, are just some samples of typical products that are used and designed for electric motors. On the left side, you see very typical parts that are very often used now for modern actual flux motors, either at the bottom, single-sided ones for auxiliaries like water pumps, oil pumps, or fan motors, or something like that, or above you see a stator component which can also be used for something what we call a jokeless motor. And you might have all seen a quite popular publication from one big German OEM, which is going to use such components in an electric motor in the future. On the other side, we also have materials which are much finer, so very smaller particles, then used for passive components like inductor parts and filters in the electronics or DC-DC converters and such applications, either in the automotive application or even outside in charging stations. That is what we see in the moment quite regularly, also in a change coming from other materials into SMC material. And actually, then I'm done.
Oh, well, yes. Hello. You were quite fast. I see already there are some questions. I will switch to the Q&A. I have maybe a comment, and maybe you can say something on this. Maybe we could say something more about the comparison in terms of magnetic properties on one hand, and what I think is also one of the, let's say, critical points probably is the mechanical properties compared to, okay, laminated steel, of course, but also other solutions, maybe.
Yes. Okay, so on the electromagnetic properties, on the, let's say, what we call basic materials, so a laminated steel with a certain thickness of, let's say, 0.3, 0.27 millimeter material, SMC material is very competitive. Only on very, very thin, high performance material that is then extremely thin and also very complicated to manufacture and with a very high scrap rate, which has been confirmed by many companies to us. Then, of course, SMC at the moment, with the material that is available by today, we do see some challenges. But on the other side, the development of SMC has not stopped. Based on the targets from the market, there's also a continuous development on new SMC materials for the future to meet the expectation and to meet the performance that is requested by the market to compete against very high performance electric motors. It is actually, I think, very well known that nearly everybody, the electric motor manufacturers, the designers, the material manufacturers, everybody is twisting and tweaking their possibilities to get higher efficiency out of the motors, and the targets, of course, getting higher and higher. The mechanical strength is of course a certain issue. Absolutely, because the mechanical strength due to the manufacturing process is lower than if you have something made out of a block of iron. Absolutely. But still, and we measure the mechanical strength in TRS, so it's a 3-point bending. Because if you do a normal tear test, already the mounting in the machine could damage the test sample.
Yeah.
But we see also here improvement for the future to get higher strengths. What we do see very often in electric motors now is that the components get potted anyway. So there will be, let's say, there will be a kind of potting process with some plastic components, which gives additional mechanical strengths.
Support.
So this is what we see quite regularly, which is not even not a request then from us as a material supplier. It is a design feature that is foreseen from the electric motor the designer and developer.
Okay, thanks. There are a couple, 3 questions actually. One is very simple. What does 5P mean?
Okay, 5P is one of the families, the SMC families that we have. We have, in the moment, we have 3 families, 1P, 3P, and 5P. The deviation is more or less the 1P is a very basic material, which can also be heat treated by normally atmosphere. The 3P material was developed specifically for higher mechanical strengths and need an additional steam impact during the heat treatment in the furnace. Okay. And the 5P material was then later on developed as a family, as a group. So there is not only one material as 5P, there is a group of materials grouped together in this family, and they are developed to have lower losses to compete against laminated steel.
And then there's Monica asking, how does porosity influence the final properties? Is there a critical level that should not be reached?
Sorry, can you repeat that question?
How does porosity influence the final properties? Is there a critical level that should not be reached?
No, not really. Actually, we don't see this as a big issue. No.
Okay. And there's another question from Covadonga. Hello, Dirk. How can we determine how the shape of a part affects the electromagnetic properties, and how can we improve these properties with heat treatment?
The shape, of course. Yeah, that's that's extremely important. What we learn actually sometimes very painfully is that the shape of the part is generated by the simulation team. So the electromagnetic simulation team, they design as a kind of first draft a potential design, and out of that, unfortunately, what we see very often is a certain design loops in the discussion to optimize then the design, because very often the first design proposals is impossible to be produced. So then you need to teach and coach them how the part has to be changed the right design wise to be producible. And then, of course, the simulation has to be run again to see if that has any negative impact. Optimization of the design is extremely important. And I can tell you that we've seen many times that designers and development companies come to us and say, hey, we have a design which was originally made for laminated steel. Can you do a one-to-one with SMC material? And unfortunately, we have to say, this is not the way that you should actually work. You should then start to redesign it in a way that SMC is optimized.
Definitely.
Yeah.
So co-design is key here.
Absolutely. And this is the lesson that Högen has learned over the last 2 years. And this is why we are working now so close with the designers. We need to influence them on a very early stage. We always say that it is not good that when a customer comes along and says they have frozen the design already and here's the drawing, then it is by far too late.
Yeah. Okay, I don't see any more question from the audience. Yeah, there is a thanks for this answer. I don't know if there are any other questions, maybe for in general for the speakers, also for the previous speakers. Otherwise, maybe we move forward to the test. Is anyone willing to ask anything else to Dirk or to the previous speakers? Apparently not. Okay, so thank you, Dirk, again. Also for bringing back all us to the schedule. We are even ahead.
I tried my best.
Yeah, okay. Thank you again. So I will switch back to the original setup and go back to my slides for the rest of the session.